logarithms. What is a logarithm? So a logarithm is the opposite of an exponential. If you think about all of our operations so far, if I add, I have an opposite to it. I can subtract. If I multiply, the opposite is to divide. If I square something, if I put it to the power of 2, I can square root it. Well, in the same way that when I put something to the power of, the way that I can get rid of that is through taking the logarithm. This is the relationship that exponentials and logarithms have. So if I have a value a to the power of y equals x, the logarithm, or the opposite of it, is that log of that same base, so a remains, of the answer is equal to the power. So an example of this is that 2 to the power of 3 is equal to 8. So I can rewrite this, I can change it or take it to the other side by saying that it's log 2, so the same power, so the same base, to the answer, which is 8, will be equal to my power, which is 3. This is very useful in trying to solve exponential equations where I need to take the base to the other side. So I will take it over by creating a log. So for example, 17, if I say that this answer, the answer I'm searching for is x, remembering the rule that if I have log of a certain base will give me an answer, well, log of a certain base will give me an answer. That answer is the power to the base to give me y. So here I've got log 2, 16 is equal to x. Well, that's my a here. This is the y, and that's the x. So I can rewrite this as 2 to the power of x, so 2 to the power of the answer will give me that inside number. Now I know that 16 can be rewritten as, 2 to the power of 4, so again trying to match the bases, and therefore x will equal 4. I can do the same with part b if I make that equal to x, so remembering that it's the base 5 to the power of whatever that answer is equal to the inside value. Now we're going to try and match the bases. So 125 can be rewritten as 5 to the power of 3. Therefore, x will be equal to 3. Let's practice that concept a little bit more. For example, 18, we're going to write the following expression in index form. So first we have to change it over into index form and then solve for x. So again, remember it is the base, so 3 to the power of the answer is equal to the inside value. So this time x quite easily is 9. Again, base to the power of the answer on the other side is equal to the inside value. Here the powers match, therefore x must be equal to 2. The base to the power of the answer is equal to the inside value. Hopefully you're getting the hang of it. 5 squared is 25. Take the 3 over. Now before I can touch the log here, I have to take the 1 over to the other side because I can't use this rule when I have something else that's in the way. So this time the 1 is in the way. I'm going to take that over. So 2 minus 1 is just 1. And now I can conduct it. The base to the power of that answer is equal to the inside value. Again, base to the power of that opposite value of the answer is equal to the inside value. Now again, I'm trying to get them to match. So can I write 64 as something to the power of 3? Yes, I can. It's 4. And because there's a negative here to make it match, I can take it to the top. So that will be x to the power of negative 3 equals 4 to the power of negative 3. Now the powers match, therefore x must equal to 4. Again, base, power, inside value. I want the powers to match, so can I rewrite as 125 as something to the power of 3? Yes, I can. That will be x is equal to 5. And again for g, the base x to the power is equal to the inside value. This will be equal to something squared, because I want the powers to match, and that will be 4. Therefore, x is equal to 4. Just like we have index laws, we also have logarithmic laws. And just like we've spoken about, exponentials and logarithms are opposite of each other, which means the index laws and the logarithmic laws are opposites of each other as well. Take, for example, the first index laws. That's a base to a power. When I multiply it by the same base to another power, all I have to do is add the powers. Well, the opposite of that is that when I add two logarithms, I'm going to multiply the inside values. In the same way, with our index laws, when I divide, I subtract the powers. Well, this time when I'm going to subtract two logarithms, I'm going to divide the inside values. This here is a very cool and useful rule that when I have a log and the inside value has a power, I can actually take that power out the front. We're going to use that quite often. When I have a fractional value on the inside, 1 on m, that can be rewritten as negative log of a on m. The way that that works is that I can write 1 on m as m to the power of negative 1, and then I can simply take that negative 1 out the front using the previous law, which is where I end up with negative log am. Using my index law, I know that anything to the power of 0 is 1, therefore log of 1 is equal to 0, so the opposite. And I also know that any value to the power of 1 is equal to that same value itself. So log a of a is equal to 1, and this is a very important rule, that whenever you have a base and a value that is the same, that will always equal 1. So let's practice it through simplifying. Remembering our first log law, whenever I'm adding two logs, all I have to do is multiply the insides. When I am subtracting two logs, I need to divide the inside. And when I have a log that has a base and a value that are the same, it equals to 1. Now, obviously 2 and 8 are not the same, but I can rewrite 8 as the same value. So I can rewrite 8 as 2 to the power of 3. Now, remembering our log law, we can take that power out the front. Remembering that log 2 of 2 is just 1, so that will leave me with 3. Now these steps here, in fact all of these, are steps that I'm not going to be going through in the future. So in the future, I'm just going to go straight from this step to this answer because log 2 of 2 will cancel out and it'll leave behind the power. Let's practice it with a few more. So this idea again, I can rewrite this as 5 to the power of 3. Now log 5 cancels out, and when the 3 comes out the front, it will be left over. 64, I'm trying to write it as a base of 2. Well, that's 2 to the power of 6, and I also want it to go to the top, so that will be 2 to the power of negative 6. 2 to the power, log 2 of 2 cancels, that will give me negative 6. Now, 0.0001 can actually be written as 10 to the power of negative 4, so think of your scientific notation. So that's log 10, 10 to the power of negative 4. Log 10, 10 is just 1. That leaves over negative 4. I can apply it to a few more rules. So here I can see that I am adding these two inside values, so I'm going to multiply them, and then I'm dividing these two logs. Oh my god. So here I can see that I'm adding these two logs, which means I'm going to multiply these inside values, and then I'm subtracting, so I will be dividing the inside values. So that will be log 2 3 times 6, and that's minus log 2 5. 3 times 6 is 18. And then I will be dividing. That should be a G. There's not much I can do to simplify log 2 18 on 5. For part B, very similar, except now I've got values out the front. So before you can type the log, I need to bring these values back so they are a part of the log themselves. Otherwise, I can't add or subtract. So this will be log 2 3 squared plus log 2 3 cubed minus log 2 5. Again, I will be multiplying the inside values and dividing these. Before I did it in 2 steps, this time I'm just going to do it in 1. So 3 squared is 9, 3 cubed is 27, and that is all divided by 5. So So that would be 3 squared times 3 cubed on 5. And remembering with my indices, when I multiply two numbers of the same base that have powers, I will add those powers there. Now you can work out what 3 to the power of 5 is, but it's quite a large number, so I'm just going to leave it as it is. With part C, I don't like the square root. It doesn't look very helpful. So instead of writing square root a, I'm going to write it as a to the power of a half. So this will be log a3 minus log a to the power of a half. Now if you remember your rule, whenever the base and the value are the same, that's just 1, and that leaves over the power, which will be 3 minus a half, which will be 5 on 2. Finally, with part D, we've got a very similar situation where I need to bring the power out the front. So that will be log 2 16x. And again, I can see that I can make these match. So 16 can be rewritten as 2 to the power of 4. So this will be 2 to the power of 4x. And 8 can be rewritten as to the power of 3, 2 to the power of 3. Make sure that you put brackets if there's more than one term. Now I can add these two logs, which means I can multiply. Oh, no. Now log 2 of 2 cancels out, it'll leave over 4x. Log 2 of 2 cancels out, it'll leave over 6 minus 3x. So that's just this expression but expanded. And now I can simplify this. 4x minus 3x is 1x plus 6. Last lot of examples. This time what we're going to do is we're going to be solving for x. So not only simplifying but also solving. So for part A, I can see I'm adding the two logs, so I will times them and then subtracting, so I will divide. So this will be log 10, 4 times 5 is 20, on 2x is equal to 2. Now this is where my rule that I initially was using comes back in. So the base to the power of that answer is equal to the inside value. So that's 10 to the power of 2 is equal to 20 on 2x. 20 and 2 cancel out, that gives me 10, and 10 squared is 100. And now I can swap these over. Multiply by x, divide by 100, gives me 10 on 100, which is 1 on 10. For part B, I can multiply these inside values. 3 times 2 is 6. And now I can see that log 10 and log 10 match, which leaves that the inside values must equal each other. For part C, we've got the base to the power of that answer is equal to the inside value. 5 squared is equal to 2x plus 3. 5 squared is 25. Take the 3 over and then divide by 2. Same idea here, I'm subtracting, therefore I'm going to divide these inside values. And then use my rule. The base of 3 to the power of that answer is equal to my inside value. I'm going to multiply over the 2, so that will be 6. So it's not the power times 2, it's just the actual value times 2. And then take that 2 over to give me x is 4. For part B, I'm going to take this 2 out the front first. Now I can see I've got log 10 on both sides, which means that the insides must be equal to each other. I'm going to take this x squared to the other side, which leaves over 6x plus 8 is equal to 0. Therefore, x will equal, I'll take the 8 over and divide by negative 6. That will be 4 on 3. Finally, this last one for part F, there's actually a couple of ways that you can go about doing it. I'm going to do it as it is over here, but what you can also do is take this log over to the other side and then solve it from there. Both will give you the same answer. Now, if I'm going to solve it without transposing anything to the other side, what I can notice is that I can't touch this side because I've got a 1, I don't have a log. What I can do is I can take this 2 out the front here, first of all, so I can unlock this log. And secondly, I can rewrite this one as a log so that I can use it. Remembering the rule that log a of a is equal to 1, well, I can go backwards. I can rewrite this one as log 10 of 10 is equal to 1. So instead of writing 1, all I'm going to do is write log 10 of 10. So that will be log 10, 10 plus, and taking that 2 up to the top. Now, because these are being added, I can multiply the insides. And because both of them are log 10, that will leave that the insides must be equal to each other. I'm just going to start expanding straight away. And I can see that I have to solve a quadratic, so I need to get everything to one side. So I'll be taking the x squared over and the 1 over. So 10x minus 1x squared is 9x squared. And then 10 plus 1 will be 11. Because this is a non-monic quadratic, what I have to do is think of two numbers that multiply to give me 9 times 11, 9 times 11, which is 99. So two numbers that multiply to give me 99, add to give me 20. Those two numbers will be 9 and 11. Sorry, there's meant to be an x here. So I can rewrite this as 9x plus 11x plus 11. Collect the like terms and factorize by grouping. These brackets are the same, so I can factorize that out. And that leaves over 9x plus 11. That will give me x is equal to -1 and x is equal to -11 on 9.